All right. I want to just take a quick look here at a little bit about probability experiments. And this is because the way that things should happen in the real world and the way that they actually happen are not always the same. Right? It would make sense that if I flip a coin 5 times, they're not all the same. Right? If I flip a coin 10 times, I should probably get about half of them heads and half of them tails. But it is possible that they are all the same. All heads are all tails. And so when we look at this idea of experimental versus theoretical probability, experimental probability is essentially the results of actually testing probability in the real world. So I flip a coin 10 times, I get 7 heads and 3 tails. That's the experimental probability. I say 7 out of 10. And then theoretical probability is the way the results of testing probability not actually, but should be. All right. Those are not the same definitions you'll see in your textbook, but that kind of gives you the gist of what's going on here. So we've got the results of actually testing probability in the real world, and then we've got the way the results of testing probability should be. So let's compare. All right. So summer camp. Counselors have created an obstacle course. Each camper must travel through the obstacle course one at a time. Halfway through the course is a fork in the path. Campers must choose to go either left or right. Halfway along each fork is another fork. Campers must again choose to go either left or right. If you imagine in your head, this looks sort of like a tree diagram. Andrew flips a coin twice to model the possible choices of any camper. A head indicates left and a tail indicates right. The following chart shows the results of 100 pairs of coin flips. All right, so he's got head and head, which means 2 lefts, 22 out of those 100. Okay, head and a tail, left and right, 24. Tail and a head, right and then a left, 27. Tail and a tail, 2 rights, also 27. Okay, those are his experimental results. All right. So from the data, the experimental probability of taking 2 left turns, so probability of left, left is going to equal, that's a lovely equal sign, the outcome that we want, that's going to be the 22, the 2 left turns, out of the total sample space of 100. And we can, leave this as a 22 out of 100, 22%, 0.22. All right. Theoretical probability of taking 2 left turns. Well, we can look at this a couple different ways. We can say, well, tree diagram, right? Initially, we can make a left or a right. And then we continue going along, and again, we can make a left or a right. And then at the end of the right, we can make a left or a right. Now, if I'm going to make 2 left turns, left and left. And so look at that. Well, that's one way to do that. So probability left, left is going to equal 1 out of a total of 4 different possible outcomes. All right, now we could change this, all right, change this to a percentage. This is going to be 25%. So not quite the same as our experimental probability. Close, but not right on. Now, the question you got to ask yourself is, if we did, instead of 100, if we did 1,000, do you think the experimental and the theoretical would get closer? And the answer is yes. The more trials you conduct, the closer experimental and theoretical get to each other. But you have to remember that if we're doing this experiment, so if we're actually flipping these coins, right? I flip head and a head, tail and a tail, head and then a tail, whatever. The one that I just flipped has no influence on the one that's going to flip next, right? The coin doesn't remember what you last did. All right, so let's move on, look at another quick example here. Spencer uses a spinner to check the experimental probability of having a two-child family with 2 girls, 2 boys, a boy and then a girl, or a girl and then a girl. All right. So he made a lovely little spinner, and GGBB. So first of all, what does BB represent? A boy, then another boy. All right. Right, just like BG would be a boy, then a girl. GB would be girl, and then a boy. GG would be girl, and then a girl. What is the experimental probability of a family having 2 girls? So we look at GG. All right, so the probability, experimental probability, GG, is going to be equal to 26. Okay, that's our favorable outcomes. And then we want to look at the total possible outcomes. And I'm going to pretend I don't know what the answer to the total sample space is. And so we're going to look and see, well, we have 26. We're going to have to add all these numbers up, right? Plus 27 plus 22 plus 25. All right, so if we add all those up, 26 plus 27 is 53. 53 plus 22 is 75. 75 plus 25 is 100. So I'm going to have experimental probability of 26 out of 100. All right. So 26%, if we wanted to change it to a percentage, we can do that. You're going to have to stay on your page, but I don't have to. I have the whole screen to work with. All right, anyways. So probability of 2 girls. Okay, favorable outcomes. That's what we're looking for, 26. Total outcomes is, yes, 100, but we can get that by adding everything up here. All right, so let's move on. Calculate the theoretical probability the family has 2 girls. So again, tree diagram. We could have a boy, or we could have a girl. And then after we've had a boy, next kid could be a boy or a girl. And after a girl, we could have a boy and then a girl. All right, now if we want to look for 2 girls, well, this path down here, right? Girl and then another girl. That's probability of a girl and then another girl. Going to be equal to 1 out of, and again, total outcomes is going to be 4, which again is going to be 25%. All right. Nothing super challenging with these. The difference here is that we're always going to have to compare. And again, why is it different in terms of experimental probability versus theoretical? Theoretical is how it should be. If everything works out perfectly randomly, real world, it's messy, right? We always have stuff that happens that may or may not follow the probability. And that's because, again, if you look at this result, each time you spin the spinner, you have a 1 in 4 chance, I guess, assuming that all of the spaces are equal on the spinner. Each time you spin that spinner, you have a 1 in 4 chance of landing on any of them. Now, the question that you got to ask yourself then is, does the spinner remember? And no, it does not. Okay, so no different than flipping a coin. If you're doing a fair coin flip, if you're spinning this thing fairly, you will have a 1 in 4 chance every time, but that might not translate exactly into a 25% experimental probability. And that's really where this takes us. So you've got your assignment I will give to you. It is on those pages, but the assignment will be up on the board. Have fun.